So let's now try to kind of generalize this thing and and like write down what's the formal condition when it works and when it doesn't work. So this will be maybe not the most general possible setting, but a little simplified. Yeah. So when defined, Newcombian problem with horizon H is the following datum. So it's some kind of term mu that takes a horizon H policy. So that means something that has like less than H observations and with reaction. Also takes a sequence of actions and observations of length less than H. And the action, and this is the distribution over observation. Right? And we assume that there's also some kind of void function, or void function, which is from a times r to the power of h to 0. So we kind of think of this as something that happens. We kind of think of an episodic setting where everything repeats after some horizon H. We could also consider some kind of a non-episodic setting, but then we would need some kind of a communicating condition. And right now, if you want to think about what the correct communicating condition in this setting is, might be also a good exercise for someone. And to understand what's the communicating version of this. But for now, we'll just do the episodic version.
Is it possible to remove the A's in the other factors if it's a deterministic policy, or do we need them for?
This is not a policy. This is specified.
But the first,
you say it already knows the policy.
Yeah.
Yeah. I mean, yeah, sure. Yeah.
And the last one.
Okay, there you go. Yeah. Fair enough. So this thing is an Newcombian problem. It tells you basically, if in the beginning of the horizon this is the policy which you're going to follow, then like this is how your distribution over observations is going to look like. Right? Could also, an equivalent way to say it would also be just to write here arrow into delta of h. Could also do something. Okay. So Now, given such a Newcombian problem, we can construct an associated ultra-POMDP. Okay, so the associated ultra-POMDP mu. So, okay, so the state space would be, so let's call this thing pi h. So the state space would be pi h times small h. Okay. And the observation mapping, well, the observation mapping would be it's like for any state like this, just outputs the last observation. Oh, I guess there's some technicality here because there's an empty string also, so we need to assign some observation to it, but it doesn't really matter when the observation is assigned to it. And the transition kernel. So what's the transition kernel? So now we take some we take a thing like this, and in action, and we need to say what is, we need to like specify, in general we can specify some kind of an ultra contribution of the states, right? So here, there's like multiple cases. There's multiple cases. So first of all, if the action is exactly what phi says the action should be, and we haven't reached the end yet, so n is smaller than h minus 1 or something like that, then we just need to apply mu and append it to the thing, right? So, let's call it graph phi and star to mu of phi. Right, where graph, so graph of phi from 0 to n applied to some q, it's just equal by definition. You just append this q in there. Okay, so if we haven't finished the episode yet, and the action is the action that is consistent with this policy phi, then we just apply mu to know to get a distribution of what the next observation is, and then we just append it to this thing we have here. Okay, this is just something that appends. Now, Okay. If we have already, if n is already in the end, then it doesn't matter, then we just reset to the beginning. So then we just output like delta over, no, then, right? Then we output the top of by h times lambda, right? So what do I mean by that? So top, top and final is the same. But I know the same as, I just, my solution is right in the top, right? This is my solution, okay. Okay, so recall the top, A, it just means consider like all the contributions whose support is in A, okay? So if we reach the end, then we reset to the beginning. And when we reset to the beginning, we can ambiguously choose any policy we want.
Yeah.
So we look at the set of the subset of the state space that corresponds to all the policies times the empty string of observations, and we ambiguously go there.
The n equals h equals 1 just means like n is 1 not h. Or and it calls h minus 1. Now, okay. Now what if n is smaller than h minus 1, but a is not equal to pi of this thing? Then, this is one case, second case, third case. Then, we just output 0. The 0 thing. This is bottom, basically. Bot of S. This is the thing that has the 0. Okay? So that's if I define an ultra-POMDP.
Sorry, but what's what is?
So mod S is just the ultra contribution that only has 0 in it. The bottom. What is good about this? Okay. Now there is some theorem. So first we need the pseudocausality condition. So condition pseudocausality. What are these conditions? The condition is that there exists a policy by H which is optimal for nu. So I haven't really defined what it means optimal for nu, but I think it's kind of obvious, right? Or it's not obvious. Like optimal for nu just means, if I just plug this policy in here and then I just follow it, then what I get is like the best expected reward I could get, right? This is just what it means. So there exists a policy which is optimal for nu, such that such that for any other policy in pi h, if nu pi equals to nu pi bar, so this thing is something in like distributions over actions and observations, right? Yeah.
Mm-hmm.
If nu pi equals to pi bar, then no, sorry, this is not what I intended to write here. No, this is not what I intended to write. But if nu pi is equal to nu pi bar, this is not what if nu pi is inside the, we got some notation for it, how do we call it? C, I think, pi bar? C pi bar? Then pi bar is also optimal for C. So what is this C pi bar? So C pi bar is, the subset of, so this is all H in A times O. H such that H is compatible with pi bar. Right, so we look at histories of length H, which are compatible with this policy. So it means whenever there's some action that appears here, this action is what this policy would recommend. So what I meant to write here is support of this is a subset of this. So again, we look at the set of all policies of histories of length H, such that this history is compatible with the policy pi bar. And we say, suppose that pi bar has such the property that the support of nu pi, that nu pi is also all supported here. That the outcomes of pi interacting with nu look as if they could be generated by pi bar just as well. The pi bar might be different as an architecture. Then pi bar is also has to be optimal. So the condition says there's no suboptimal policy such that the outcome of the optimal policy looks as if it might have been generated by the suboptimal policy. Okay. So now the theorem says if this condition, if pseudocausality holds, then okay, and
So I find it a little surprising that this depends on the reward somehow, I would think. Of the.
I mean, it has to depend on the reward because otherwise, like the empty I mean, the empty dependent Newcomb and the full box Newcomb are the same. So there is like a stronger version of the condition which wouldn't depend on the reward, but it would still like hold in most cases in some sense.
Mm.
So you could say that this is like reward independence instead of causality, right? Reward for like a pattern independent causality. I mean, terminology is not the best. So the reward independent condition would be that, okay, that for any policies pi1 and pi2 in pi h, if the support of new pi1 lies in C pi2, then new pi2 equals new pi1. Okay. This doesn't depend on the reward, and it's sort of, but for example, so in transparent Newcomb with noise satisfies this condition, but without noise it fails this condition, and it doesn't matter if it's empty box dependent or full box dependent. But if you do this condition, then it holds for the empty box and only fails for the full box dependent.
Thinking of terminology, that would be called pseudocausality, and that would be like pseudocausal optimality or something, where there's just the optimality that's...
Yeah, yeah, I guess, I know. Well, later we can invent better names for this.
It's a support subset equal of the C pi. It's just like, I don't get the intuition, of why that's like enough. Seems a bit weak. And
so this condition says that this condition guarantees that Murphy cannot mispredict you, because for Murphy to mispredict you, so you're following the policy pi. Okay. Now, if Murphy predicts correctly, like Omega should predict, then you will get the optimal reward that you deserve.
okay.
But maybe Murphy will cheat. Maybe Murphy will say, no, I predict that you follow some other policy, pi bar.
Okay.
But in this case, so if the support of nu pi doesn't lie in C pi bar, then it means that Murphy will get caught in the line. Because then there is some probability greater than 0, then something will happen which is not consistent with pi bar, and then the loss will immediately go to 0. But so then Murphy cannot cheat. But if Murphy finds a policy such that the support is contained in it, then it won't, then it can predict this policy and not be punished for it. And then only if this policy is also optimal, this will stay. Otherwise, there's good. Okay, so if this holds, then what? Then, then first of all, the minimum reward, the minimum loss of this ultra-POMDP is the same as that of mu. So the minimum over all policies of the expected loss, expected with respect to m, mu, and pi, loss times k parameter gamma, will approach the minimum overall policies of expected respect to mu pi L gamma as gamma goes to 1. And second, for any policy, the expectation on mu of the loss will be upper bounded by what happens on the ultra-POMDP plus some function of gamma, where this function goes to 0, gamma goes to 1. Okay, so the optimal loss is going to be the same in the gamma to 1 limit, and also, as long as you're following the policy that's actually maybe this is too strong, maybe just for the optimal policy. Yeah, I think what I meant to write here is actually, maybe this is overstated, and the way I stated this condition is, I mean, this would be true for this condition actually, but here just for the optimal policy. So like if if pi gamma is such that the expected loss with respect to mu pi gamma is the minimum loss. Goes to 0. Then it's also true for the actual mu. So if I have some family of policies that's optimal for the ultra-POMDP in the gamma to 1 limit, then it's also optimal for the actual POMDP.
There's a gamma that shouldn't be there on the second to last line under the expectation. To the right, in the minimum, that's not pi gamma, but just pi, right?
Yes. Yeah, I guess if we took the reward independent condition, then we would get a stronger conclusion that for any policy that gets some loss, you would get a similar loss. So, whatever.